like Amanda said, this webinar is called Block Cycle Test Creation in nCode GlyphWorks. My name is Joe Spadola, and I'm an applications engineer for HPM nCode, and I'm based out on the West Coast. Today, we're going to be talking about how we can use a piece of software called nCode GlyphWorks to create a block cycle test. And what we'll see, of course, is that the block cycle that we're creating, this simplified test, isn't arbitrary. Okay, we're not just pulling a test spec out of thin air and running with it. Clearly, we need to put a little thought into it and how we create it. So what we're going to do is take advantage of some unique features in GlyphWorks to intelligently design our block cycle test spec. And when I say intelligently, what I mean is that we need to come up with a way to ensure that this simplified test that we're creating is representative of actual in-service customer usage. Okay, and what we'll find out is that we can do that by establishing a common link that makes theoretical sense from a fatigue perspective between the customer usage data and our simplified test. And I'll go ahead and spoil the surprise right now and tell you that the common link we're looking for is damage. And we'll be using GlyphWorks to calculate that damage and then to ensure that this newly created test spec contains the identical amount of damage as the customer usage data. Okay, so with that said, the purpose of today's webinar is to see how nCode GlyphWorks can be used to create equivalent damage durability test specifications. Okay, so a lot of words there. Let's think about this test article in white here for a minute in this picture. This is a shock tower that you'd find on some sort of ground vehicle, and so as you drive this part around, you'll see loads from the shock, or the damper, the strutter, or whatever it is that connects up to the body in white there. So what we want to do, or what we want to find out, is how we can create a test that utilizes this very simple test rig, which here it just has a simple actuator like this. So we want to create this test that's still representative of in-service customer usage. Okay, how can we reproduce those loads in this lab environment in a simplified manner, such that we can validate our part here in the lab without having to drive around the test track for thousands and thousands of miles? What does that simplified loading spectrum look like? And again, how do we make sure from or in a fatigue sense that this test is in fact equivalent to driving around for, say, thousands of miles or whatever it is? How do we ensure that this means something useful? Okay, these are all very important questions, and we'll spend the rest of this presentation seeing how we can answer those questions within GlyphWorks. So this is our agenda for the next 30 minutes or so. I'll start by giving a brief background on GlyphWorks, which I assume this audience is relatively familiar with, or at the very least has a working knowledge of. Then I'll talk a little bit more in detail about this concept I've already discussed a little bit, and that is this idea of equivalent damage calculation. Okay, how do we ensure that this new test spec has the same amount of damage as our infield damage? Okay, and then I'll finish up with a live demo so that you can see everything that I'm talking about here in action. So we'll actually get in the software and click around a little bit. Okay, so I want to give you a quick background on the software itself. As I said earlier, I assume that most of you out there are probably already familiar with GlyphWorks, but I wanted to just take a second to formally introduce it to you again, or for those who've never seen it, to introduce it to you for the first time. GlyphWorks is one of 3 software products developed by nCode, and it serves as a data processing system designed for analyzing measured test data. nCode has 2 other products. One is called Design Life, and Design Life serves as a fatigue analysis tool in the CAE domain, and it effectively turns whole model stress plots into life plots. Okay, so that's kind of the basis of Design Life. Our third product is called Automation, and it serves as a database for storing and managing large amounts of test data. The unique feature about automation, however, is that GlyphWorks lives underneath it, and it can automatically process data as it's uploaded to the automation server. Since our focus today will be GlyphWorks, I'll dive a little bit deeper into its capabilities. So, as I've said already, GlyphWorks is a data processing system designed to analyze measured test data. It has a powerful and easy-to-use graphical interface with drag and drop capabilities. We can deal with data in both the time and frequency domain. The processes that you can create are easily scalable and can handle without problem very large channel counts. We're talking hundreds to thousands of channels, as well as huge numbers of tests as well. It also has something called one-click reporting capabilities, which allows the user to efficiently and automatically generate reports of customizable results. GlyphWorks also has a wide range of built-in DSP tools like filtering and mathematics and stats and signal editing, conditioning and anomaly detection. It has a vast array of built-in fatigue analysis capabilities as well, such as stress life, strain life, and crack growth. And we'll see a little bit of that today, or a subset of that today. And we also have a variety of tools for noise and vibe analysis. This is only a relatively small subset of all of GlyphWorks' capabilities. We have over 100 built-in and highly configurable engineering functions, or what we call glyphs, that are ready to use. The goal of this webinar is not to give an intro to GlyphWorks. So if that's what you're looking for, I do suggest you check out our full list of webinars on our website, as we do have a number of more introductory webinars out there. This one is not one of them. Okay, so let's get back to this idea that I mentioned earlier, called damage equivalence. Okay, so whether we like it or not, the parts and components that we as engineers design are going to experience quote-unquote real-world loading. Okay, and this real-world loading is going to be highly variable and is going to happen over a very long period of time. An amount of time that we can ill afford to spend validating a new design if, as a company, we hope to stay competitive in today's world. Okay, so that is to say that it's completely impractical to have to validate our parts by just putting them out in the world and letting people use them as normal, right? We want to be able to validate our new designs, or we need to be able to validate our new designs with a much shorter, much simplified test that we can do right in our lab. Furthermore, we need to ensure that this new test that we're creating is actually representative of real-world use. Okay, so how can we ensure that passing this new test we create in the lab means that we can guarantee that we will survive our customers in service usage? Okay, the answer, of course, is damage. So think about this guy here in the picture dangling from the helicopter here. Somewhere there, he's attached by a hook, kind of like this right here. So we can throw a force gauge on the hook and measure the force history of him performing some sort of real-life maneuvers or something. So that real-world loading history, indicated here by the red squiggly line, is going to cause some amount of damage. Okay, so his moving around and rescuing people and lowering down the cable and the helicopter movement, all of this stuff is going to cause some amount of damage. Okay, and By damage, I mean nothing more than the amount of life of the part that's used up during this or due to this fluctuating load history. Okay, once we can accurately capture that damage value, we are then free to create our simplified test. Okay, we simply have to equalize the amount of damage due to our test and the amount of damage here that we just measured due to this red squiggly line. Okay, thus ensuring this concept of damage equivalence. Okay, so we've calculated the damage of our in-service loading. We know that we can do that. Now, what we need to do is create this simplified test that I keep talking about. And there are a number of different ways in GlyphWorks that we can do that. Okay, if say you actually want to, for whatever reason, replay an entire recorded time history, we can do something called fatigue editing in GlyphWorks, where we compress a recorded time history by simply removing non-damaging content from it, at which point we can then replay it on an RPC test rig. Okay, so we're looking at the third box here. If we want to run our part on an electrodynamic shaker, we can work in the frequency domain with a feature in GlyphWorks called accelerated testing. Okay, these are both viable options in the right situation. However, today we're going to be focusing on creating a simple constant amplitude test and a logical extension of that called the block cycle test, both of which we can do inside GlyphWorks as well. The constant amplitude test is exactly what it sounds like. It's a test that cycles back and forth between constant values over and over and over and over again. Okay, very simple concept. And the block cycle is just a series of constant amplitudes strung together. Okay, so you know, some large cycles, some not so large cycles, just strung together, and you can kind of see that indicated by this picture here. A block cycle test can technically contain any number of cycles and any number of given amplitudes, but again, the point of this is to create a simplified test. So, you know, at a certain point, overcomplicating the block cycle spectrum can become counterproductive. So the idea is to create something representative, but still simple and easy to recreate in a lab. Okay, so again, we have our in-service loading history, and we have our simplified test. Our simple cyclic test is quick, it's easy to set up, it's inexpensive, and it's pretty much used everywhere. Okay, so the only thing that we need to do is this damage equivalence. Okay, we need to calculate the in-service damage and figure out how many cycles of a given amplitude are required to cause that amount of damage. Okay, so we first pick an amplitude as representative of the real data, of the in-service data. So how hard are we going to be pushing and pulling back and forth on our part with, say, this simple actuator test here on the right? Okay, that's our first decision. Then, with that and our known in-service damage, we can calculate the number of times we need to push and pull our actuator here. So how many cycles until the damage is equivalent. Okay, so that's how we go about creating this simple test. We pick an amplitude that makes sense. It's a value that is or is close to the max amplitude seen in our in-service history here on the left. Okay, and we know our in-service damage value, and we can easily calculate the amount of damage due to one of our single simple cycles at our chosen amplitude. So all we have to do is simply ratio those damages, and what we're left with is the number of simple cycles, so the number of these cycles on the right here, required to equalize that damage, to equalize these two damages, okay? And for this reason, you can see that we don't want to pick an amplitude that's too small. or will be causing such little damage or even no damage per each of our simple cycle that it'll take a prohibitively large number of cycles to equalize these damages. Okay? Again, the point of this is to save time. And on the flip side of that, we don't want to choose an amplitude so large that we equalize our damages in fractions of a simple cycle, right? Because this could lead us to a different failure mechanism, which is obviously not the goal of this either. This same concept can be extended into the virtual world as well. Okay, it's not really practical to run a complex FEA analysis with, say, for example, contact or something like that with an hour's worth of measured data just to see how the part behaves over time. So rather than applying a super long force history, we pick maybe one or two forces that are representative of our in-service loading that allows us to accurately capture the part's stresses. And then in design life, which, as I mentioned earlier, is the CAE counterpart to GlyphWorks, we can then simply cycle back and forth between those two forces, and this will drastically speed up our fatigue analysis. Okay, and it will also allow us to run a much simpler FEA solution as well. So time savings all over the place. Okay, so I'm going to jump into the software real quick and show you a quick demo of what we're talking about here so that you can actually see it in action. Okay, so what I have here is a preloaded flow. This one here is extremely simple. So I keep talking about this concept of damage equivalence. So this word damage keeps popping up. The first thing we need to do is be able to calculate that damage. So all I'm going to do right now is simply show you how to do a very simple damage calculation. For those of you who haven't seen this GlyphWorks before, this is the user environment here. On the left here, you have a list of available data. Okay, this is data that has been loaded into our the data that we are able to work with. We pointed to that folder here. So anything that GlyphWorks finds in the folder we're pointing to will automatically be loaded into our available data window here. This means that it recognizes this data. It's data that is available for use inside of GlyphWorks. On the far right, we have what's called the glyph palette. This is what contains all of our engineering functions. So here we'll see we have our list of basic DSP tools here, and we've got a series of fatigue tools here. We've got display tools. Okay, so all of those glyphs I was talking about earlier, all of those engineering functions are contained within this glyph palette here over on the right. Okay, in the center, where we see this grid paper, this is where our process comes together. So we've got some input. Okay, this is going to be our input data. We've got our fatigue calculation. This is a relative fatigue calculation. Okay, very simple SN calculation. And then I've got a display box here. This is going to show me the results of that fatigue calculation. So at this point here, I have my process ready to run. I have the glyphs here connected by these pipes, so I know where the data is coming in. I know where the results are flowing. I know what glyphs are doing the calculation. So from this point, all I have to do is drag and drop my in-service measured data. So this is my loading data from some in-field experiment. Okay, I can zoom in on this and actually take a look at it. So here you can see I've got about, what is that, about 4.5 minutes or so worth of data. Okay, this is the load history, and you can see, in fact, it is highly variable. Now, what we want to do is create a simplified test that represents this loading here in a much simpler way. So, like I said, the first thing that we need to do is figure out how much damage is contained in this load history right here. So that's all that this flow does. All I have to do is simply send that data to my damage calculator, and the results here pop up in the metadata display on the right. Okay, if I look at the results of that glyph, I can see here is my damage value. Okay, and again, this is a relative damage value, meaning that we're not doing an actual strain life calculation per se. We're not doing an absolute strain life calculation because we don't have stresses here. We're just looking at loads, of course. Okay, so this is the damage value that we're after. So I'm going to go to my next workspace here. Okay, I've created another workspace, and this contains a flow that has a couple more glyphs on it. But this one will actually do the damage equivalent calculation that I've been talking about. Okay, so here again, I'm just going to grab my my beam load, so that same force history that I just saw. Okay, I'm going to bring it into this workspace. So same exact force history, 4.5 minutes of measured loads. And this glyph right here, let me just run this real quick and then I'll walk through it. So this glyph right here is what's allowing me to create my simplified cycle. Okay, so you can see what's coming out of this glyph is a very simple constant amplitude single cycle. Okay, so this is the simplest case, one single cycle at one amplitude. This is what I want to represent my my in-service history by. Okay, so what we're doing here, we're taking the in-service history, we're combining it into a single test with my simplified loading. Okay, we're letting this potential damage, this relative damage glyph, do our calculations for us. Okay, just like we saw earlier, this is telling us how much damage is occurring because of this, and it's also telling us how much damage is occurring because of this. And like I explained earlier, the way that we figure out how many of these we need to equal this in a damage sense, we simply ratio those two values. So that's what this display is showing me right here. Okay, here's my test cycle amplitude. So 850, that's my amplitude. Okay, and if you remember, that's exactly what I put in here. So an amplitude of 850. I have my field damage. So this is the amount of damage due to this entire load history here. Okay, some value. And again, this is not an absolute value. This is a relative value. And then I know doing the exact same thing to this cycle here, I can figure out how much damage we have per test cycle. So that's for one single 850 Newton amplitude cycle, this is how much damage is occurring. Okay, so like I said earlier, I have the infield damage, I have the test cycle damage, I've chosen my amplitude, and with all that information, I can simply calculate the number of test cycles required to equivalence those two damages. Okay, so again, this is nothing more than the field damage divided by the test damage. Okay, and that ratio is 204, which means that if I want to recreate the amount of damage caused by this, I simply need to run this test here 204 cycles. Okay. I have a Rainflow histogram here okay, or a Rainflow counter here. This is going to do nothing more than extract the cycles in the loading history, as well as my test cycle. Okay, so if I look at this a little bit larger, I'm going to put these on the same scale here. Okay, so this is Rainflow histogram. It's keeping track of all the cycles in both of my channels there, the infield history and the test cycle that I did. So you can see my infield history has a range all the way up to about 2,300. So the maximum range found in my loading history is right around 2,300. Okay. So the test cycle that I created had an amplitude of 850. Okay, so that's a range of 1,700. Okay, so range is nothing more than just double the amplitude. Okay, so you can see this amplitude here falls at about maybe 75% of the way up to the maximum amplitude seen in our test, or in our infield loading. Okay. So what I want to do now is create a simple extension of this. I want to actually create a block cycle and make this slightly more representative. So we have one cycle, and you can see where this falls in the spectrum of the in-service loading. Okay, so I'm about 75% of the way up to the maximum one. So what I want to do is pick a couple more cycles or a couple more amplitudes that fall within this range as well. So if I look down here, I'm going to pick some smaller cycles, maybe one around, say, an amplitude of 500 or a range of 1,000, and then a range of 500 or an amplitude of about 250. Okay, so I'm going to create a new input load or a new test cycle that contains the same 850 amplitude cycle, as well as a couple different ones. Okay, and I can do that by just replicating this time series generator here, this waveform generator that I used to create my first cycle. Okay, so I'm just going to copy and paste. Okay, and I'm going to rename this so that I know what I'm doing here. This one was 850. I said I'm going to go to 500, and then I want to create another one that is about 250. Okay, so I'm just going to rename these. And now I actually have to go into the properties of these and modify them such that they are actually those amplitudes. So here's my start amplitude. It was 850. This one I said I'm going to make 500. And this one I said I'm going to make 250. Okay. So now all I have to do is connect all of these cycles together. Okay, so we do that. I'm going to do a little rearranging around my workspace here. In GlyphWorks, to do that, we're going to use something called the concatenation glyph. The concatenation glyph just sequences the two inputs that you give it. So I've got my 850 amplitude. I'm going to send it to the concatenation glyph, and then I'm going to send my 500 amplitude cycle to that glyph as well. So I'm combining these. Not in the superposition sense, but I'm combining them one after the other. Okay, so if I go into the properties here, I can control how many times each of those are repeated as well. And let's say I've got, I want one of the large cycles, and I want, I don't know, 3 of these 500 amplitude cycles. Okay, so I can tell it to repeat that second signal that I give it 3 times. Okay, and then I'm just going to copy and paste this again and combine the last one. So now I've got these two combined, so I want to combine those two to this smaller one over here. And in this case, I want, say, 5 of the smaller ones. Okay, this is obviously this is an extremely manual way to create these cycles, or this block cycle. There are a lot of other ways in which you can do this. This is just a quick and easy way to show it, to show how you would do this live here. Okay, so from this, I'm just going to run this as it is, and then show you what we've done. Okay, so now you can see my simplified test is slightly more complicated than last time. Okay, here's my 850 amplitude cycle. Okay, you can see I've got one of those, and then I do indeed have 3 500 amplitude cycles and 5 250 amplitude cycles. Okay, so now this is my my block cycle. From here, it's extremely simple to do what we just did for the single amplitude that I did earlier. I'm sending this exact same block cycle into the same flow that I had earlier. Okay, so I've got a Rainflow counter, and if I look at the Rainflow results, you can see again I have the exact same results for my infield loading, but now let me put this on the same scale again. Now you can see here's my 850. Okay, I've got one of those. And then if I look, I can see now I do, in fact, have a couple more cycles in my test block, or my block cycle, okay? Here you can see I've got 3 of these at an amplitude of 1,000, sorry, an amplitude of 500, or a range of 1,000. And then I have 5 of the smaller cycles that I created at an amplitude of about 250, or a range of 500. Okay, so I'm getting a, as I build this block cycle, I'm getting a more accurate representation of the actual loading here. You can see I've got some number of cycles here on the lower end, some number of medium cycles, and then one of the larger cycles. Okay, and that's representative of the real data here, because as you look farther out or far higher in the ranges, you can see I have a few of these, slightly more of these, and quite a bit of these. So I'm trying to replicate this loading here in a simplified way. Okay. So once we do that, I simply send that data to the potential damage glyph, or the relative damage calculation. It does the exact same thing it did last time. It's calculating the field damage, okay, same exact value. And now it's giving me a damage per test cycle. Okay, now this test cycle isn't one of these. This is this entire history now. So this is damage due to 1 large cycle, 3 medium cycles, and 5 small cycles. Okay, so the result here is slightly smaller than the one before, and that should be correct, and that is correct because I have more cycles that I'm doing to replicate this in-service damage. Okay, so that is a simplified way of, or a sort of on-the-fly way of creating this block cycle. There are a number of different ways in GlyphWorks in which you can do that. You can create, you know, you can make these as complicated or as simple as you want. This here is a simple version. You can create one with something called our schedule create app over here, which is an interactive way of creating these as well. And then you have an actual file that you can use among different flows or different processes. You can send them to colleagues and stuff. Doing it the way that I just did it necessarily embeds this in this particular flow. Okay, so if you wanted to make this portable, there are a number of different ways that you can do that. This here was just a simple example to show you what it actually looks like. It's the best way to kind of visualize this block cycle that we're creating. Okay, so like I said, number of different ways that you can create those block cycles. This here was just a simple way. So I'm going to jump back into the presentation now, and I should mention that what we were doing was a relative damage calculation. Okay, clearly we were looking at forces, and if you know anything about fatigue, you would know that you can't take a force and go to an SN curve, okay, because an SN curve should be stress and not force. If you do have stresses, you can do an actual damage calculation with an actual SN curve. If you choose to keep it the way that we did it right here, it's perfectly valid because the calculations that we're doing are relative, so it's an apples-to-apples comparison. Okay, so To sum things up, we have our in-service loads, okay, here on the left, and we have our simplified test spec here on the right. And what we really need, what we're really after this entire time, is some way to make sure that our test spec is valid. Okay, something that links the two of these together. And of course, that answer or that link is damage. And we've seen how we can use GlyphWorks to calculate that damage. Okay, and there are a number of different ways in which we can do that. We saw one of them here today. And then we also use GlyphWorks to help us define the important parameters of our test spec. So that important parameter was the amplitude. Okay, so you remember we chose that amplitude. We also then used GlyphWorks to calculate the number of those amplitude required to reach this common link, to make those two damages equal to each other. Okay, thus ensuring that we have an apples-to-apples comparison. Okay, and again, this concept does have a parallel in the virtual world. The key here is that in FEA, we need to do whatever it takes to accurately capture our stresses, wherever they come from, be it contact forces or thermal forces or nonlinear loading forces or whatever it is. We need to get these reliable stresses. Once we have that, we can apply a simplified loading history, okay, greatly simplify our fatigue analysis, and consequently achieve a reliable fatigue result. Okay, so capture accurate stresses, apply a simple loading history, and once we do that, we can trust. We know that we can trust our results. Okay, so